phi will vanish there. And so that gives you 0, B theta, and B phi. Yes, which is also when you're, if you remember doing a lot of stuff with conductors, not only does the transverse component of the conductor vanish, transverse component of the electric field vanish on a conductor, the electric field is normal to the surface of any conductor. And one additional piece of information, a conductor is an equipotential. So all three of those are the same thing in electrostatics, and they're also the same thing in the potential field source surface model. Okay. But this comes out of the lecture. You've seen this. This is how those things actually look. This is a typical example of one of those potential field source surface models. The blue lines are the last closed field lines. So there's a ring of null points, of X points around here. By the way, they don't use image charges for this. They use spherical harmonics. If you guys remember going from junior level E&M, where you're using image charges, to graduate E&M, you started using spherical harmonics, Y sub LM. You get the same, you get similar answers. That's just a more sophisticated technique for doing it. And I'm going to leave it there because we need to take a little bit of a break, and then we need to come back for the second part of my marathon. Okay, I'll end there, stop sharing, and let everyone have, should we say 10 minutes and come back at 10 minutes of the hour? Or, yeah, that should be enough.
Yeah, for those of us who are on the hour, so.
Yes, those of us who have that. Okay, I'm gonna need to zip out, but I'll be back to answer some more questions in maybe 3 minutes. I need to make a little.
What is that?
Oops. Let's see. Um, okay. I think someone here, Andreas,
Oh,
was
yeah.
asking if you could use a more complicated shape. I don't know if he's taking a break or.
Yeah, I'm here.
Oh yeah. So you mean for image charge problems?
Yeah, so I mean, now you're assuming that you have this radial field in a sphere, but since the magnetic field, you could like maybe what if it was like oval shaped?
Yes. People have done that. So first of all, I don't know if you were asking about image charge tricks because I teach this.
Well,
The
the trick is
amazing
gonna
thing
be
is
harder,
there's
obviously.
actually no other shapes that I know of that I've ever seen that you can do image charges with. One could argue it's just a sphere and then consider a sphere to be a plane to be a sphere of radius infinity. But if you just want to solve Laplace's equation inside an ellipsoid of some kind, it is possible. And people have done that. What's really remarkable is, while I know that, I don't know where they've published that, and I don't know of anyone who's ever used it. Everyone uses this spherical source surface model, as far as I'm aware, or they go to full MHD. But in principle, yes, you can solve Laplace's equation inside ellipsoids.
Would it
In
be?
fact, I think if you go to, of course, Landau and Lifshitz, their electrodynamics of continuous media. I'm looking over to my bookshelf to see electrodynamics of continuous media. Of course, being Landau and Lifshitz, the very first chapter is solving Laplace's equation in ellipsoidal coordinates. So there are ways to do it.
Because that's the most intuitively obvious way to do it.
No, it's because once you've done it that way, you know, everything else is a special case, right? The spherical coordinates, well, that's just a special case of ellipsoidal coordinates. Cartesian coordinates are just the cylindrical coordinates. Yeah. Anyway.
Okay.
Yes. There are those people who work by intuition and those people who just are able to do everything all at once. Oops. So I guess I could, just talking to Nick here and maybe, well, everyone else can hear. I have the slides that I used for this, which I can also post. They're sort of adaptations of the slides that were posted before. This has the activities in them, but otherwise.
For the last
Yeah, what I was just doing.
That would probably be valuable.
Okay.
Since you've got your solutions.
I have my solutions, and it continues on past there. We didn't get to it. This is what I've always learned about teaching is, you know, I could try to cover more material, but that doesn't mean people learn more things. So.
I think we've got a couple of minutes before we start. And Deb
Yeah. But.
Yeah, so I have a question. So it's regarding the Heliosheath region. So in the Heliosheath region, we saw that the rho goes high.
Yes.
And so the B also, because in the Heliosheath region, we have the V, which is higher compared than the VA, the Alvin speed, right? So
right. So
opposite one actually. So
right. So this is, I know I promised you we would talk about this
yes.
once we got to here. And so what happens is you get this shock. And the reason the thing shocks is basically it has to be information coming from outside. There's nothing, the solar wind cannot know about anything ahead of it while it's going supersonic. And a shock is just basically running into an obstacle. And when you run into an obstacle, all of a sudden you learn about that thing. And the way you learn about it is in a shock. So the one thing that happens in the shock is the flow speed drops. And in sort of a standard hypersonic gas dynamic shock, it will drop by a factor of 4. The
speed dropped by a 4, right?
The speed drops by a factor of 4. Then the density to conserve mass has to increase by a factor of 4. And if the magnetic field is going sort of perfectly transverse, which it more or less is there, that will also increase by a factor of 4. So the magnetic field strength increases by a factor of 4.
Okay.
Yeah.
So I have another question regarding this. So for the reason of a shock, we need the Mach number is higher compared to 1, right?
Correct.
Supersonic. But is it the only reason? Because I saw in some of the articles that sometimes the advective terms in a equation, in the force equation, the amplitude of the pressure actually high, so that the amplitude steepens. So is it the same thing, means the pressure amplitude actually steepens and then we can have a shock kind of thing?
Yeah, so what you're doing is talking about the how you start from having a flow that doesn't have a shock, but it has some large scale, some large amplitude variation, and then that solution steepens into a shock.
Yes.
That's a time dependent development of a shock. And that would not happen if the flow was everywhere subsonic. Essentially, those variations would propagate as sound waves, and they would never steepen.
Okay, so inherently it is actually Mach number is higher compared to 1.
Yes, to develop a shock, you need the Mach number to be greater than 1. And in MHD, of course, it's much more complicated because you have to say which Mach number, the alpha Mach or the beta. Yeah, it gets pretty tricky, but the rule of thumb still applies. It's when you're exceeding one of the signal speeds was when you can shock.
Yes.
Yeah.
So,
and my favorite version of that is to say that a shock is a hydrodynamic surprise. No information can come from ahead. And so the fluid just basically has to run into this shock in order to, and what it does is it slows down, but even more importantly, at least in the hydrodynamic case, the temperature goes way up. So the sound speed goes way up. So on the other side of the shock, the flow is actually subsonic. Then it knows about the stuff ahead of it. And this is going to come up also when we talk about magnetospheres. We're going to have exactly the same, oops, who's that? I don't know who this is. Nick, are you seeing this? Sorry, there's something.
I am not seeing anything. What am I looking at?
Oh, there was someone who was looking to get into the room.
Oh.
Okay.
I admitted them.
Okay, good. Thank you. All right. So I think we're back, right? Is this correct?
Yes.
Yes. Okay. Yes, I see 42 participants. So I am the next speaker as well, and I am going to switch over from, I guess I do know something about the corona, a little tiny bit about the solar winds, but I'm going to talk to you now about solar flares. And this is not so much a review. This is a more specialized lecture, but you saw the version of it I gave, boy, 4 years ago, I think. Does anyone have any questions on what they've watched on the video? No questions coming up. All right, well, this is going to be less, I do want to hear questions. I do want people to interrupt me, but we're not going to have any activities or breakout rooms. That was more for the overview kind of thing. So this will be a little less interactive in that way. And I will, oops, share that screen. Okay. Can everyone see that? This is the same title I used before.
Yes.
Yes. Okay. So here is the place I like to start, and that is what a flare really is by definition. And I think Bill Murtaugh pointed this out. It is really identified in this day and age by the flux of X-rays. And here's a plot from GOES. We've been talking about the GOES satellite. And at this particular time, 2002, the 1 to 8 angstrom band was sort of fluctuating around 10 to the minus 6 watts per square meter, and then suddenly jumped up and then came back down. And you can see it jumped up and stayed up for, it took about half a day to come back down. That is a flare. And if you zoom out, you see all these little spikes. They look little because now I've zoomed out for an entire month, the whole month of April. And there were lots of these little excursions, and they go up by different amounts. So each one of those is a flare. Okay, not a big surprise. Here's a different flare, but what I want to show here, the very top panel is the GOES X-ray flux. I put the watts per square meter on the right, but on the left, I put the fraction. I don't go out far enough, but there's a background level. And I show you how much it's enhanced by above the background. And you can see it just goes up to almost 100 times background. This isn't even an X flare. So this particular band of X-rays, the brightness of the sun in that wavelength goes up by a factor of 100. Now, if you go to some of the extreme ultraviolets, and these are the ionization states we talked about, you can see we get nice iron 18. That is shown, that comes from an Eve channel. No iron 17, sadly. But that goes up by, basically, it doubles in that wavelength, whatever wavelength that is. Iron 20, which is sort of 10 million Kelvin plasma, the emission in iron 20 lines go up by a factor of 10. And as you get to cooler and cooler lines, they increase above their background level by smaller and smaller fractions. By the time you get to the far ultraviolet, this is one I'm going to talk about a lot, 1600, we're really only talking about a 2% increase in the brightness. Okay, but importantly, every wavelength that we're looking at here brightens to some degree. Okay, and that is a flare. And here, this is not from Bill Murtaugh's talk, but another talk very similar to it, showing what the societal impact, what the space weather impact is of a flare. And this is the big Halloween flare that he was talking about, October 28th, 2003. And here, the GOES plot, this is on a linear scale, and it's not based on the right, it's scaled. But I will tell you, the X-ray flux has gone up by a factor of 300. This is one of the very few flares, maybe the only, no, I think there's been a few others where they could actually see an increase in the overall luminosity. All the energy from the sun has gone up. There is the solar irradiance, the so-called solar constant. It increases by 10 to the minus 4, okay? So in that sense, it's not a big increase in the brightness of the sun, but in the X-rays it is. And here we saw many plots of total electron content. That was also something that you guys looked at for your lab. You can see that when this X-ray brightness goes up, the total electron content on the Earth goes up. So it is this brightening. That is the one part of a flare that really has an impact on Earth's weather, of a flare. Now, here is some images of that, not the Halloween flare, but this flare here, which is sort of an M flare. I want to start with, this is a magnetogram. Many people saw images like this. The plus, the regions where magnetic field is coming at you is white, where it's going away from you is black. I'll draw your attention to this magenta line, which was actually drawn, it might be drawn by hand. It is the polarity inversion line. It's what separates positive from negative. So field lines go from the white across the magenta line to the black. And you can see in the bottom two panels, these are images made in 2 different wavelengths, and you can see those field lines. I've drawn in, well, in neither case have I drawn in the magenta line, but I've drawn in the blue and the cyan lines. And you can see that these loops go from blue to cyan, or actually they're going from cyan to blue, okay? So the field lines that connect from positive to negative are visible in a flare. One of the things you might notice though, if you look at the times here, this is all sort of around, well, this is the peak of the flare, 1250. So the loops are being seen later, and we'll get back to that. Here's the FUV, barely brightened at all in the dark blue. These are all reverse color tables, by the way, because that's the way I like to do it. I have put in the magenta polarity inversion line, and what you see are these two long features that are more or less parallel or fall along the polarity inversion line. Can anyone just shout out, just unmute yourself and shout out the name we give these long features that are parallel to the polarity inversion line at the peak of a flare?
Flare ribbons.
These are flare ribbons, thank you. These are the flare ribbons, and we'll see. This is a very important part of a solar flare. Finally, I'll just draw your attention to these yellow contours. This is actually from the RESI spacecraft. This is I think it's 25 to 50 kilovolt photons. These are gamma rays. And you see that they're concentrated just at one part of the flare ribbon. Basically, the flare ribbons are the foot points. So I've reproduced the magenta and blue lines. Those are the foot points of the field lines. A few of those field lines are hosting gamma rays. They all come from the feet. All right. I have to show everyone's favorite flare now. I call it a typical flare. It's the September 10th, 2017 flare. It's the most photogenic flare I think we've had. And the reason I like to show this is it actually has 2 things going on. You see the flux rope, you see this bubble shoot off to the right. That's a coronal mass ejection. That is what you're going to talk about tomorrow. We are not going to talk about the coronal mass ejection. The stuff to the left, where you see all this brightening, that is what I said, a flare is a brightening of the sun. That coronal mass ejection does not make the sun any brighter at all, so it's not a flare, just by definition, right? And so from this wonderful image here, I've turned them around, but one of the reasons everyone loves this flare is you see this sort of shape in, I think this is in 195, AIA 195 or 193 angstroms. It looks a lot like this cartoon. This is what's known as the standard model or the CSHKP model of a solar flare. And in blue are magnetic field lines in this cartoony type model. And in this circular thing up here, that is the coronal mass ejection. That's the bubble we see take off. So in the standard model of a flare, it's sort of confusing, but a CME is kind of part of the story, but it is not the flare. The flare is this part down here in the bottom. This is where the brightening happens. So this is really what the flare is. And it has a few aspects to it that are worth noting. You have magnetic reconnection going on at this X point. You have plasma flowing in and field lines flowing into that X point and then shooting back out. And they shoot out along this long ribbon, and it's impressively long in the September 10th flare. Not ribbon, outflow jet, we'll call it. It's an outflow jet. Again, there's our favorite shocks. And then you see this emission coming from what's known as an above the loop top source. And even more important are these loops underneath. And those are the loops that we see. This was on the limb, so it was easy to see the whole movie. These loops here, these little striations are those loops. And that is really what the flare is. That is, the flare is all the emission coming from those loops. Okay, and down here you see the ribbons are the things at the feet of those flare loops. So we've been talking about the ribbons. Okay, so that's the standard model. I want to now talk about 4 things that go on in this flare model. So I've gotten rid of the CME. We're not going to talk about that anymore. The first thing that happens in this flare, or the first step in a flare, is that magnetic energy is released. That's the reconnection part. You bring the magnetic field lines together, you reconnect them. I'll show you in a bit what that really means. If I don't know if Amitava can hear me. If he does, he should probably mute me right now, because I will tell you there is no energetic significance to what goes on in this X point. The reconnection process itself does not have any energetic, does not release any energy. I will say that. It enables the energy to be released, but the energy release occurs in this long outflow. That is where energy is converted from magnetic to other forms. Okay, so that is the magnetic energy release along this outflow. Then when the energy has all been released, it ends up getting transported down from high in the corona down to these feet where the ribbons are. That transport process is important, because before that transport happens, you don't see any ribbons, then you see ribbons. The ribbons are, I'm going to make the case, this is the most important part of the flare. This is where we get what's known as chromospheric evaporation, and we're going to talk quite a bit about that. That is where plasma is boiled or ablated or evaporated. You know, all these are bad terms because there's really no chemistry going on here. Up into the corona. It raises the density of the corona a lot. And as we've seen, the radiative losses go as the density squared. So that, once you start doing the evaporation, that's when you're going to see the radiative output of the flare, and the thing that we associate with a flare is that. That is the part, and that's the part that has consequences for us. And then finally, once that material's up there, it's going to sit there and it's going to radiate and it's going to cool. Okay, so there's the 4 parts. I'm going to focus on the evaporation. That is where all the X-ray brightening happens. And the loop cooling, these 2 parts are most of the observations. Some people have been able to image things like these above the loop top sources and things. They're difficult to image. Most of what the observations I've shown you so far take place in steps 3 and 4. And so that's where I'm going to really focus my energy, but my efforts. I'm going to talk about this release of magnetic energy. Now, one thing I will ask for a little feedback. I'm sorry, we zoomed through stuff this morning, but you did this calculation where you found that for this loop in an active region, the volumetric heating rate, and here I've rounded up to 10 to the minus 3 ergs per centimeter cubed per second. And the density was about 10 to the 9. These are rounded up numbers. That was a static loop. My question then is, using these scalings, someone can just shout out the answer. If I increase epsilon by 10,000, by a factor of 10 to the 4, how much roughly is the temperature going to increase if I stayed in these equilibrium scalings? We're going to see these actually, while it's not in equilibrium, these scalings are pretty useful for understanding flares. So I go from, you know, this amount of heating to something that's 10,000 times larger. 10 ergs per cubic centimeter per second. Anyone, how much is temperature going to go up? You can just give me a
10 power 14.
10 to the power 14. Look, epsilon here. Anyone? It's epsilon.
Oh, sorry. I'm sorry. I did the opposite way. Well,
no,
2 by
I did
7.
that.
I should
10
do
to
2
the
by
power.
7.
10 to the power what?
10
it's
times?
8 by 7.
Yes, to the power 8 over 7, which in my books is 1. So it goes up by basically 10, right? So the temperature will increase by a factor of 10.
14.
Only
Yeah,
14, in fact.
Yeah.
I did actually use a calculator for that one, and I think I got that right. So the temperature goes up, right? And if it was 3 million, now it's like 30 million or something. That's kind of impressive, but that's, you know, not giving us a 100-fold increase. or even more. The density, that's the important thing. The density goes as temperature squared. That goes up by 16 over 7. It goes up by a factor of 200. And the output, the radiative output, if you just use the NE squared and you don't take the temperature dependent, goes up by 30,000. So again, just like with the coronal loops, one of the important things to remember is when this energy is released, it heats the flare, it heats the plasma a bit. I mean, 14 isn't trivial, but it's hardly 30,000. It raises the density. That's the important part of a flare. That's the reason it gets so bright, is the density has gone up so much. Okay, all right. Let's see. I think in the interest of time, I did this in the lecture that you saw. I'll play the movie so everyone can see it, but I'm going to kind of skip over it. This is the beauty of a flipped classroom, is you kind of skip over these things. And this is just arguing that where the energy comes from is basically turning these field lines that go over top of the CME and therefore have to go up on one side of the current sheet, come down on the other. Reconnection breaks them and adds them to the loops below. And if I count the amount of flux in the loops below, that's this black curve. Okay, that's the amount of flux, and that flux increases. So the ribbons actually move outward away from the polarity inversion line. That shows me how the flux is being reconnected, how many new closed loops are being created over time. Now, the thing that's a little harder to get your head around is the total current in that current sheet goes down. As the flux goes up, the total current goes down. And then you can see, I always teach these undergraduate E&M classes. The amount of work done is the integral of the current deflux, okay? That's the area inside this curve. That is all the energy that's been released by magnetic reconnection. I'm not telling you how, I'm not telling you how it's converted to any other forms, but I just know this formula because I teach it to freshmen and sophomores. This is how you calculate the energy done by an electromagnetic field. And the place that really comes into play, here's an even more two-dimensional flare that we're looking down on. Even better than the September 10th flare, but doesn't have nearly as many fans. This is what I call the Boxing Day flare, 26th of December. People from the Commonwealth will recognize that date as Boxing Day, the day after Christmas. But most importantly, you see the ribbons on the left. This is our 1600 angstrom image. And then on the right, you see all these loops forming, connecting the footpoints of their footpoints are the ribbons. And actually, this is from work that tomorrow's lecturer, Dr. Zhong Chu, has done, and I've worked with her a little bit on it. If you take the magnetic field measurements, you can see the ribbon, and the colors here show you where the ribbon was brightened at a certain amount of time. I think it's 15 minutes past the hour, 25 minutes past the hour, 35, 45, 55, up to red. You can see the blue to red goes outward, away from the polarity inversion line. This is exactly the way the ribbons are moving, okay? So if you take all of the colored pixels and add up the amount of flux, that tells you this part of the energy calculation. That tells you this black curve here. This is the flux as a function of time, and that should tell us the energy. Well, we also need to know we need to know the current, and for that, again, I go back to undergraduate physics, and I say, well, if I have an inductor of length 7.5 times 10 to the 9 centimeters, then the current is related to the flux, basically by flux over length. The great thing about CGS is I don't have any mu naughts, it's just length. That is the inductance. And so I can calculate, this is the amount of flux that was reconnected. This is the phi as a function of time for the Boxing Day flare in the red. The blue, in case you're interested in electric fields, is the time derivative. You get up to 10 billion volts drop in this. but I don't know what the drop is across, but you get this amount and you calculate the energy. This is the energy released in the Boxing Day flare, 10 to the 31 ergs. And you just get it from calculating how much work was done in transforming field lines that used to not connect to field lines that connect. Okay, so that's everything I'm going to say about the release of energy, because the real action, as I tried to indicate, is when this energy enters the flare loop. Okay, so we're going to skip over the part where the energy is actually added, and I'm going to put in an ad hoc source, H, and that stands for steps 1 and step 2. All the parts that have to do with magnetic reconnection, conversion of energy, it all ends up getting sucked into something that says, I'm going to add 10 to the 20, 31 ergs of energy to these flare loops over, let's see, I can see this goes from about 11:15 up to noon, maybe 11:45. So over half an hour, I release this amount of energy. That tells me how much H is. I'm just going to add that to a loop. Imagine that it's staying static now because we're done with the release of energy. And I want to find out what happens in the evaporation and the cooling part, because that's where all the effects of a flare are going to come from. So the second most sophisticated version, you can do this whole thing as an MHD model, but what has been very useful for people is to take this one-dimensional object, this tube, parameterize in length from 0 to L, the total loop length, has a cross-sectional area that varies along the length, and you solve for the continuity equation, conservation of mass. This looks a lot like what we did with the solar wind. Really are the same equations. We have conservation of momentum. Here's some viscosity in there just for good measure. And here's the energy equation. And we see some of the same actors we saw before. We have thermal conduction. That's going to be very important. And we have radiative losses. And then we have this heat source. And this is the enthalpy flux. Well, this and this will combine to be the enthalpy flux. So that all goes in. This, if I solve this, this would basically be solving for functions of two variables, space and time, space and time, space and time. This is called a 1D flare loop. For the amount of time we have left, I'm actually going to go to 0D, because I'm going to talk about not the distribution of mass density, velocity, and temperature over space, but I'm just going to do the total integral of all the mass that is from some, and I will talk a little bit more about where I call the end of the loop. It's something called the transition region. But the important thing is I have a region and I integrate all the mass that's in that loop. And the mass evolves basically if there's flow across this boundary. Okay, so the increase in mass has to do with the density at that boundary times the velocity times the area, right? That's no surprise. Then we have the total energy, and we have to include the kinetic energy and pressure. This is the 3/2 NKT, which is the pressure, the thermal energy. It turns out for all of this stuff, especially in a flare, the gravitational potential energy is irrelevant. That was a big part of what we did with solar wind. Gravity is very important when you're trying to escape the sun. This is just filling a loop with hot plasma. So the time evolution of the energy, if I basically integrate this equation here, and my own students will tell you how much I love to integrate by parts. There's quite a bit of integration by parts that goes on here. I'll just show you the end. The total energy in this bit is going to decrease due to radiative losses. It's going to increase or decrease by enthalpy flux. That was very important in the solar wind. And then you'll have this flux across the transition region of thermal conduction. And then here's the input, here's the heat. So there's 4 terms that contribute. There's also the kinetic energy flux. That's always small, so we'll stop talking about that. But the whole story of a flare boils down to how these 4 terms play together. Okay, so just a quick back of the envelope calculation. This is the input energy. It is the heating, but integrated over length. And I think I encouraged one of the groups when they found that H, which in your exercise was called epsilon, same thing. You integrate that over length and you'll get a flux. That is the amount of heat energy per centimeter squared. Here you're multiplying it by A, but that's going into this flare. We calculated the electromagnetic work. It turns out you can turn that into B squared over 8 pi. Zeta here is just meant as a factor of order unity, times the Alfvén speed. This is basically how fast the retraction part is going to release energy. Because the field lines are getting shorter, their magnetic energy is decreasing at this rate. You put in that, you put in this, you get sort of 3 times 10 to the 11 ergs per second per centimeter squared. This is sort of the numbers you got for your exercise were of this order, 10 to the 7. So this is sort of a 10,000-fold increase in the heating energy that's going in. That's why I use that number to illustrate things. You can see the amount of energy coming out of a flare is comparable to the solar luminosity. Now, we already commented that you get a lot less brightening out of a flare than the solar luminosity. That tells you right now that there's going to be a lot of inefficiencies in how this magnetic energy that's released at this rate is translated into radiation. It doesn't really dominate this, but it can, give you sort of 1 part in 10,000 of that. So that's sort of one term that we've already dealt with. So here is the evolution equation I just talked about. We can replace the mass by sort of an average number density. That turns out to be a little more useful to work with. So an average number density, and then you multiply it by the mass of a proton and the area and the length, and you'll get these are all constants. So instead of talking about total mass, I'm going to talk about total density. And instead of talking about total energy, I'm going to talk about pressure, or pressure is basically density times temperature. So I might also talk about temperature. But the important thing is this equation and the mass conservation equation give us the evolution of the density in a flare and the evolution of the pressure in a flare. And most importantly, I was talking about the fact that the pressure is going to change, and it's got 3 things that can change it. It's going to decrease as it radiates away. It could increase if there were evaporation. So this is the enthalpy flux. It's going to decrease due to thermal conduction. And then it will increase because I'm going to add energy through the flare. Okay? So the whole point of a flare is to follow this evolution, the evolution in the total energy density, and also the evolution of the density, the mass density. Okay, so yeah, we have a few minutes and then we'll take one more break. But I want to get to part of this solution, and what we argued was one of the most important things. Well, I didn't devote any time to this, but the initial part of a flare is essentially dominated by this energy release. And so if all the rest of these terms drop out, all it does is the pressure of the flare increases due to the heating. Okay, that's the first part of a flare that sort of comes before we solve any of this. The second part, next part, is evaporation. And here is the way these things play. And one of the things, I always teach my students this, and now I'm teaching you this. We have an equation with 5 terms in it: time derivative, radiative losses, go back to this form here, radiative losses, enthalpy flux, conduction, and heating. There is almost never a circumstance where you're going to have an equation with 5 terms where every single term is doing something. Okay, and I always use the homey analogy of when you get your friends over to help you move a sofa, and there's 6 of you, and you pick up that sofa. I hate to say it, but like 4 of those people aren't doing anything, or they're doing very little, because really you only need 2 people to balance a sofa, and they're probably the ones holding the whole thing up. And the same is true for this equation. Out of these 5, 3 of these people are useless. And in fact, we're going to stipulate that the energy input has gone out. So I've actually set that to 0. And I'm going to claim that at this point, the radiative losses are irrelevant. Okay? And in fact, what's going to happen is this last term is also irrelevant. The coronal energy will not change. It is going to be a balance between evaporation and conduction, and those 2 are going to play with it. They're going to balance each other. And the cartoony picture here is the following. The red is the corona. The orange is some new bit of corona that's been heated up. And the green is that magical transition region, and blue is the cold stuff. So the thermal conduction is going to move energy from the corona into this green region, into the transition region. So it is a loss. But then there's enthalpy flux, and that is moving energy back in. And another way to think about that is moving the blue boundary downward, okay? Because you're heating up cold material to become hot material, and you're counting as a corona the hot material. So you're increasing the amount of hot material, but if the transition region energy never changes, and you can sort of see in this cartoon that it doesn't, you do not increase the total energy in the corona. You send it out through conductive flux and you suck it back in through enthalpy flux. So this actually totally vanishes, and the only 2 guys lifting this sofa are the enthalpy flux and the conductive flux. Okay, so evaporation happens as along a line of constant energy density, constant pressure. Okay, so whatever evaporation is doing, it's not changing the energy of the corona. I'll show you a nice little movie of evaporation, although it's impossible to really see the point I just made. This is heat coming in from the left, well, from the middle here, and then it's from the right over here. And this is the density down here, and you see this big chunk of density is moving down, and you see this velocity. You have some downward velocity, and then you have all this upward velocity. That is the losses. In the video you watched, I actually went into a great amount of detail about how this evaporation occurs. Right now, I'm just going to focus on the fact that it occurs in a way that keeps density times temperature constant. So I'll just talk us through this. This is a plot. As I said, we can think about this 0D model as the flare has a certain amount of material characterized by the density and a certain amount of energy characterized by the temperature. And at first, energy is added to the flare, and so the temperature increases. And it goes straight up, and it goes up so fast in this simple case that the density doesn't change very much. Then you have the evaporation. That occurs along N times T is constant. That's this dashed line. So what evaporation does, it does not change the energy in the flare. It increases the mass of the material in the corona, so you move to the right. And if you're going to keep the product of N times T constant, the temperature is going to drop. Okay, so evaporation does these 2 things. It increases the density of the plasma, and it decreases the temperature of the plasma until some magical point that we'll get to after our break. And so this is plotted as a function of time. The red is the temperature. It's going up when I add energy, and then it's coming back down during the evaporation. The density stays more or less constant during the input, and it rises during the evaporation until the evaporation ends. Okay, so that seems like a good point, and it's actually 1/2 past the hour here. So why don't I let everyone take a 10-minute break, and I will hang out and answer any questions that you didn't want to interrupt me to ask. Otherwise, just go off and, boy, as I said a long time, a lot longer than I am, a lot older than I am, smoke them if you got them. Okay?
Dana, I
in-
do have a question.
Sure.
Kind of related tangentially. So I've seen it in several places, people saying that the standard model really only works for like maybe half to 2/3 of flares. So do you know what the configuration is for the other flares that don't fit it?
Well, yeah, the full picture of a CME creating this current sheet, and then the flare being the response to the current sheet, the reconnection of the current sheet, happens. Half was probably a good number. But so there are flares that don't have coronal mass ejections. Compact flares they're called. However, in those cases still, we believe, I certainly believe, there is a current sheet. It is created in some other way. It's not by a coronal mass ejection. One of the common ways to hypothesize it's created is you have some kind of instability in the plasma, like a kink instability, that takes a current that's sort of more or less uniform distribution and then tries to make it kink up, right? That will jam two plasmas together and create a current sheet. And when you have a current sheet, then you will have a flare. So I think what people are saying is that scenario of how you create a current sheet doesn't happen in every flare. There are people out there who say maybe there's not a current sheet in a flare. That's basically saying that they believe there are ways of creating a flare that doesn't involve magnetic reconnection. That is not a widely held belief, but it's still, I can't say it's wrong. I can't say for sure. But yeah, there's I think what you're hearing is that idea of a CME creating the current sheet is really only true in and especially the larger flares tend to do it that way. Compact flares are typically smaller. Non-eruptive flares are typically smaller, both in physical dimension and in energy output. Make sense?
Yeah, thank you.
Yeah.
Dana, a quick question. In your
Yeah.
standard model, you showed this a whole series of features, and one of them was called termination. Is that termination in the corona, or is it lower? And is it?
Oh, it's in the corona. It's in the corona.
It's in corona.
It is a fast magnetosonic termination shock.
Shock. Okay.
It is a shock. It is a fast magnetosonic termination shock. It is part of the model. You probably know the same cast of characters I know. There are people who swear by its existence. Terry Forbes predicted it in 1984, along with his postdoctoral advisor, a guy you may not know of named Eric Priest.
I know that.
Yes, of course, I'm being facetious. Yes. And in certain types of MHD simulations, it does occur. There was a long period of time where no one had ever seen anything that was convincingly a termination shock. Some radio observers from what was then East Germany, it's now Germany, or us, I want to say, shoot, I'm blanking on some of the other, yeah, and it was a radio observation, and they saw something that was convincingly fast mode shock. Unfortunately, it was kind of like an hour after the flare, so it's kind of hard to associate it with that. More recently, though, using the VLA, Bin Chen observed what was quite clearly a termination shock. And he's got a Nature paper out of that, and yeah, it's made headlines ever since.
Okay.
So given how important it is and how many people swear by it, I've just listed the 2 people who have ever seen them. all the time in radio. There are interpretations of some hard X-ray features as termination shocks. That's a lot less, it's less easy to definitively call something a shock when you observe it that way. In radio, you probably know, one of the things you get access to is the plasma frequency, and the density jump you expect as shock shows up as a jump in the plasma frequency. And so you can see that in radio.
Okay.
And that's the kind of thing that Bin Chen and the Oris and those people reporting there. So that's why it's really indisputable that that's a shock, because they see that the density jump
Okay.
as a plasma frequency jump. People also like it because that's the kind of shock you can accelerate particles readily at. So if that is your favorite method of particle acceleration, you hunt around and say, where could there be a fast mode shock? And that seems to be the place. But it has even theoretical problems. You have to exceed the fast magnetosonic speed. And what's happening is you're being accelerated by magnetic tension, and you will accelerate up to the Alfvén speed. Sadly, or curiously, we never see these outflows going at the Alfvén speed. Right? The Alfvén speed would be 2,000 or 3,000 kilometers per second. If you've ever seen, I could show you, because we observed them in the September 10th flare, the downflowing plasma features. And those are going at anywhere from 200 to 600 kilometers per second. So at least half an order of magnitude lower than the Alfvén speed, if not a full order of magnitude lower. You're not going to shock at that speed. You can't shock. You're below the Alfvén speed, and that's the Alfvén speed. Your plasma has just been heated. The fast magnetosonic speed is still higher than that, and then there's component. Yeah. Anyway, I could go on and on about why I think the fast magnetosonic termination shock. I'm not going to say it doesn't happen. I should say, but I say one should always be skeptical about its presence.
Okay. All right. I had not heard of that as a terminology, so that was
Okay.
Yeah. All right.
Well,
Thank you.
Yeah, I mean, as I've tried to make clear in this part of the lecture, the evaporation is so much more important for everything that, say, affects the Earth here, right?
Right. Okay.
That is where the X-rays come from. That is why the total electron content goes up. I mean, the CME has even more consequences, but that's tomorrow's lecture. The flare itself has effects mostly from the increase in X-rays, but by a factor of 300, obviously that's a non-trivial amount of increase in the X-ray flux in hitting the ionosphere. So, yeah.
So actually, that reminded me of another question.
Yeah.
Because I've been wondering about this. Because the GHOST classification is purely, at least from my understanding of it, it's a purely geoeffective measure.
No, well,
not because my understanding of it is that it's the 1 to 8 angstroms is like the part that most affects the ionosphere.
Okay, yes.
Right?
Yeah,
which is what we measure it for.
Yeah.
So then, can you then have a flare that doesn't have, it has everything else, but it doesn't have that particular band of X-rays, but it has everything else?
Well, as I showed in sort of the lead up, every band of radiation gets enhanced. 1 to 8 is typically thermal emission. So that's from the hot plasma. The next band up, the 0.5 to 4, obviously there's a lot of overlap there, but that tends to show a disproportionate amount of the non-thermal precipitating particles, things that I actually haven't even really talked about here. And so it's the thermal part that's really reflecting the evaporation. And I guess what you might be asking is it ever possible that you have a flare and it doesn't heat the plasma up to, well,
yeah, so I guess because it seems, I mean, it seems like an odd way to define a phenomenon by a certain effect when physics is kind of more complicated than that.
Oh, I
So
wholeheartedly agree. And people who really study flares, the GOES classification is kind of like a street address or something. Just because a person lives at a 1400 address doesn't tell you anything about the people who live there, right? It does, however, there is something that's called facetiously the large flare syndrome, which is essentially once something has a lot of X-rays coming out of it, probably everything that's more physics important is also very big. Everything is big together. Yeah. So it would be nice if we could, it goes all, you could draw a parallel to the Richter scale, right? That tells you how big an earthquake is in this weird measure that they've concocted because it's easy to measure. What you really want to know is how much damage it's done. Or if you're interested in geophysics, how much energy is in it. What we would love to know is how much energy each flare has. There's no one who measures that routinely. I showed you one calculation of energy. People don't always even agree to order of magnitude of energies. But I think everyone agrees that a flare that is an X class has more energy than a flare that's an M class. So again, you're going back to, all right, this sort of sorts our flares in terms of their, big versus small flares.
Yeah, following on with to Liz's question, it looks like there are some flares that have a very large input from extreme ultraviolet. At least that would be some of the assessment from the ionosphere. But that probably syncs up quite well with large flare syndrome, and that the X-rays have gone up, and for some reason, perhaps disproportionately, there's more energy in extreme ultraviolet, and the ionosphere goes crazy at that point.
I see. Okay. All right, I think we are done with our 10-minute break. I see 40 participants. You guys don't have to turn your cameras on. I'll just start up where we left off. Any questions on what we've done so far, though? Some of us were having discussions here, but you were taking a break. Does anyone have any questions of what we've talked about so far? No questions?
We got about 40 minutes left, Dan.
Yeah, okay. Well, fortunately, we have only the last quarter of this to go, and that is after the evaporation part. The flare has gotten hot. Evaporation has occurred, and the plasma density has increased. The temperature has dropped. We have the last phase is this cooling part, where the evaporation was on the left. That is the foot points, the ribbons. The cooling is on the right, and those are the flare loops. And if you look at this carefully, you'll actually see in this wonderful Boxing Day flare, the ribbons have basically finished when you start to see all these loops, right? And there's many other ways of seeing this. The loops you see at 1 million Kelvin, which is what you're seeing here, have cooled off from that very high temperature they got to significantly. And that's the whole second part of this, the last part, I should say. So in this case, if you actually flag a couple of foot points that you say, these brightened at a certain time, 23 minutes past the hour, and then you look to see when a loop forms with those foot points, it's 44 minutes. We've seen numbers like that before. This is a typical cooling time to get from high temperature to low temperature if you're relying on radiation. So back to a different version, I apologize for that, but it's basically got the same players. We have a time derivative, we have the enthalpy flux, we have the radiative losses, the conduction. There's no input term, right? That's long gone. And now again, we have to worry about which of these terms is actually doing any good. Enthalpy flux, we said, all it's going to do is increase the, it's not going to change the temperature, the pressure, which is density times temperature. So that actually won't increase things here. I have plotted here a solution to that equation and showed you that the density increases. And then down here, you can see the temperature increases first, and then during evaporation, the temperature drops and the density increases. Okay, that's the evaporation part. And that is governed by the thermal conduction, right? That is, the thermal conduction is taking energy out of the corona, and then enthalpy is bringing it back in. So it's those two that are balancing, and that's what sets the time scale. It's what's known as the conductive time scale. It's basically a ratio of those two, and you get a time scale that goes like this. And what I've shown in the magenta arrows here is just if the curve were to go down at that time scale, it would follow the magenta arrows, and you see it does. Those are more or less tangent to the solution curve. The blue arrows are what if only radiation was important, and you see they're going way off to the right. In other words, they're showing that this plasma would cool much more slowly than it actually does. So that's a signature. The fact that these blue curves are so shallow is telling you that he's not helping lift the sofa at all. He's doing he's contributing nothing. Radiation is doing nothing during this part of the flare. But you'll see the radiative loss direction is always to the right. The conductive time drops or increases as the temperature drops. It goes as temperature to the 5/2, temperature to the -5/2. We've seen that same factor 5/2. That's a very important factor. So as the loop cools, the conductive time gets longer and longer and longer. It's going to cool more slowly. Eventually, it matches the radiative loss time. Okay. And the radiative loss scales as temperature to the 3/2. So it's a very slow process for high temperatures. And as the temperature drops, and we saw this again for the loop model, as the temperature drops, radiation becomes increasingly important, and eventually they both become important, and it's those two that balance, and the enthalpy flux stops doing anything for you. Okay, so then you have a balance between radiation and conduction. Okay, and in fact, here's the magical thing. If we say, how does that ratio, if I set that ratio equal to 1, then I get something that goes as T⁴ over NL² is a constant, or temperature goes as density to the 1/2. Where have we seen that before? Temperature going as density to the 1/2, or density going as temperature squared? We saw that earlier today. It's been a long day, but. Anyone? Temperature going as N times L to the power 1/2. I know it was written exactly that way.
Is it like the intensity?
No, that goes as N², but yeah, someone? That was the equilibrium scaling law. That was the scaling law that you used in your activity to figure out what the density was. I'm going to skip through some of these. Basically, what we're having is this enthalpy has gone, and you have only these two terms. You basically have a balance between maybe this decrease, but actually if the pressure is uniform over the loop, then this is just the same thing as if it were some kind of negative heating. We have the loop equilibrium equations, and essentially N going as T² is the same thing. Well, this is the version you saw before. T going as N times L to the 1/2. It's an equilibrium law. So remember I said, boy, you don't think a flare should have the same scaling laws as an equilibrium loop. But now you see that it does, because equilibrium loop is just a balance between radiative losses and thermal conduction. And as soon as the evaporation stops, those are the only two guys left. And that's going to dictate how the thing cools. And it's going to cool at some combination of the conductive and radiative cooling times, but those two times have to be the same. It's similar. They're not exactly equal, but they scale together. Okay, so this is a magic piece of that. I'm going to skip this here. This shows you the full evolution of a flare now. We've combined, this is the full set of equations which you can solve, and you get temperature increasing when the right-hand term is on, and that causes the temperature to go up, and very little else happens. Then, once you shut it off, once that's shut off, once the energy's been added, you have the evaporation, which goes down along this line of constant pressure. It decreases the temperature and increases the density. And then you have the line where density goes as temperature squared. That's the magenta line. And that's the flare cooling off by radiation. Okay, so that's the full evolution of a flare, in a flare loop, I should say, in sort of physicsy terms, right? So you add energy, the energy causes a lot of material to boil up into the chromosphere, into the corona from the chromosphere, and the chromosphere really. So that decreases the temperature and increases the density. And then and you'll see I used a logarithmic time scale because the heating time is very short. It's probably not 2 seconds. I did this just to illustrate. The evaporation time scale is a bit longer. That's 3 minutes in this, maybe 4 minutes in this picture here. And the radiative cooling time in this case is 30 minutes. No, this is actually, well, yeah, it depends how you count it, but this goes on for over an hour. That part of the flare is the longest lasting. That's why you see these loops when the temperature cools down to 2 million, you see it show up in some of these EUV bands much later than everything else. Okay, this is when I actually solve the differential equations. They look like this. You'll see they look very similar to that, although the corners are rounded out because it is true when you're close to one of these corners, it's violating my rule that only 2 terms are ever doing anything. You get to a point where 3 of them are kind of all doing something until you get into another phase where only 2 are doing it. You get the idea. But it shows you that you can figure out from this simple picture the peak temperature you're going to get to, the time when the heating has added all the energy and no evaporation has happened, you can get as the 2/7 power of the input flux. That's the same 2/7 power, very similar to what we saw in the loop scaling law. It shows you that a flare with 10 times as much energy input is really only going to get up to, you know, twice the temperature or something, right? It's not enormous. Now, when I put in all these numbers, this gets up to 50 million Kelvin, right? That's non-trivial, but, you know, as I said, it's not, you're not, you know, you've added a huge amount of energy. This is 4 times 10 to the 11 ergs per centimeter squared, which I added over, I think, 2 seconds or something. Then what really matters in a flare is when does the density peak? Because that's when the X-ray emission is going to be highest. That's where our GOES classification is going to come from. By then, the temperature has dropped. In this simple picture, it's actually dropped to like 7 million or something. Yeah, there it is, 7 million. But the density's climbed up from, I think it started out at 2 times 10 to the 9, and it's gone up to 3 times 10 to the 10. So you get a huge increase in the density. We saw that with the loop scaling as well. Here's a different version. There's nothing really magical about that. Now here, from all of that, we were talking about the GOES classification and how that's relevant to anything. If you follow these simple steps here, you can predict for the total amount of energy that goes into a loop what the temperature is when the density peaks, okay? And when the density peaks, that's when the X-ray emission is going to peak. That's going to be the peak of the GOES light curve, the X-ray emission. And here's how it scales with all the components of the flare. V is the volume of the flare. That actually matters. E is the total amount of energy that went into the flare. One of the things that doesn't enter into this is how long you took to add that energy. The reason is because you're assuming that you've added the energy, evaporation has happened, and it's happened basically by redistributing all the energy you added. So you don't care how long it took you to add the energy because it's just getting redistributed until you've reached this point. And then there's the peak. So when you put all this together, you actually get, and this is a handy dandy formula. It's premised on a really big if. If we're dealing with a flare that we really think is a single one of these loops satisfying, I'm going to go all the way back just to point out where all this comes from. After all my talking, it all comes from solving this equation here, or this equation is just an integrated version of these three equations, okay? So if you had a flare that just satisfied those equations and it was a single loop, then the peak X-ray flux is going to scale. The reported classification here would be go as the energy you put in to the 7/4 power, the length of the flare loop to the -1/4 power, and the volume separately. So importantly, so this is a discussion I think Elizabeth was having, but hopefully you all got to participate. Does the GOES classification tell us anything? In this big hypothetical, yes, it will tell us the energy of the flare. Adding twice as much energy is going to give you a GOES classification that is 4 times higher in this classification here. However, a real flare is not a single loop, right? We see here, I think we counted these, there are 300 loops here, or some order of that on the Boxing Day flare. And they don't all brighten together. So what really you have to think about is each of these loops is doing exactly what I said, but they're all brightening at different times. And so what you see in a flare is a composite of these. It's an envelope of these. So here's the power coming out, and here's the power going in, and here's the emission measure. Each one of these peaks at sort of its own place, and here, this curve here, is the total emission measure. It doesn't look like any of these. Each of these cools off a lot faster. So that's the warning, is you really cannot use this relationship. The relationship between what you see in GOES and what comes out is not as straightforward as that little exercise would make it seem. It really is because flares are composed of a lot of loops. All right, and yeah, I'm not going to dwell on that because in the last 20 minutes or so, I think we might end a little early so we can have some discussion or questions. We started with this picture that what a flare is this brightening in X-rays, or in, yeah, we identify it in X-rays, but it's a brightening in all wavelengths. Here is the initial month-long X-ray curve, GOES curve. And here is that one day, the April 21st. I call this the Earth Day flare. I think it's not quite on Earth Day, but that flare there. And if we just now say, okay, we've seen everything we want to see about flares, let's just use the GOES classification, these are X flares. There was one of them. This band here is, yes, not sure. Yes, okay, so this is the sort of high M class, and then the lavender color is the low M class, right? And so you see how many flares you have in the high M class. 1, 2, 3, 4. I think I've circled them. 4, yes. And then in the lavender, you have 11. I won't try to count them here, right? So you see that over a course of a month, you get 1 X class flare, 4 M class flares, 11 M medium, 4 big M class, blah, blah, blah. You probably get the idea of where I'm going from this. It tells you the number of flares per day in any range of GOES classifications. You can build a histogram of this. Many people have done this. This is just some work that Mike Wheatland did about 15 years ago. This is the GOES peak flux. We'll see, I'll show you a slightly better version of this. Better in my opinion, because I did it. But when you build this histogram using those numbers that we just did, you see that it's a power law. Okay, the peak, he calls it S. I call it F, but the number the number in any band goes as the peak flux to the minus 2.15 power. And actually, it's the integral of this that you would want to know. The classification level to the minus 1.15, that tells you that there are 14 times as many flares above M class as there are above X class. That's just from, here you can see many years of this flare statistics. You'll notice this rolls over. These are undercounted. I think, yeah, here's my favorite plot because I made it. This is a little tougher to see, but basically you see this, the year along the bottom. This is the S, the classification. So you see the blue line here is at the boundary for C class flares. This is M class flares is the green, and the red is X class flares. For the very top, just for those who like to see that, that's the sunspot number, not your social security number, sunspot number. Obviously, sunspot max, you get more flares. And what I've done here is color coded the number of flares in a given set of, I think, three month bins over some interval of sizes. And you can see that there's this dark range. Below it is white. That's the roll-off that I said. Basically what it's saying is at that time in let's look at 1989, close to the sunspot maximum, there were a lot of C-class flares going off, and anything that was less than a C-class flare just got buried in all the other flares. You couldn't see it. Okay, so that's why you're undersampling. It has nothing to do with the instrument so much as the fact that you're looking at the entire sun, and if there are too many C-class flares going off per day, then you're just not going to see anything below a C-class flare. And you can see that that bottom goes up and down because when you're between solar cycles in 1996, you saw every C-class flare. There was, any C-class flare that went on, you were going to see it, and even B-class flares, you're going to see those as well. So up here in this intermediate panel here, I show you the number of C-class flares per day. And you can see it follows the same sunspot cycle trend. During the max, you're seeing somewhere over, I think the median here is 3 per day. It gets up to almost 10 per day. The number of M-class flares in the green gets up just over 1 per day at solar max. In this last cycle, not quite 1 per day. Okay, so this is how the sunspot cycle and the this power law distribution figure in. Now, yeah, here's a, I'm not going to answer this question. Many of you may have noticed this in the literature. There are other things that look like this. This is a plot. I think I was likening the GOES X-ray flux to something like earthquake magnitude. The Richter scale magnitude is not a full characterization of how strong an earthquake is, but big magnitude 6 earthquakes are big earthquakes. Magnitude 7 earthquakes are even bigger than those. If you bin them up, you get a power law distribution as well. So there may or may not be a relationship between those. Here, this is something that I was sort of wondering, hopefully if Dolores is still here, she might have something to say about this. This is where this Wheatland work went, is if you know this power law distribution of the flare magnitudes, and it varies, right? If you'll see that the number of flares per day is very low at solar minimum, very high at solar max. But at any time, if you took a bin here, you could figure out the number of M to X class flares you're going to see per day. And you could use the power law and you could come up with forecasts. You could tell what is the probability, that you're going to see an M class flare on a given day. And this is sort of the diamonds are the observed number. So this is, I'm forgetting the name in meteorology, when you basically take past data and do a forecast, but it's of, using data from before that day to predict what you would have predicted on that day, and then comparing it to what?
Postcast.
Okay, a postcast.
Yeah.
Yes.
Sometimes it's called conditional climatology.
Okay. All right. Good. So this is basically the this is the case that Mike is showing you here. He's showing you that he could get the correct prediction for how many X-class flares there would be on a given day ahead of time. And it's just based on this power law. It's just based on the fact that if you see a lot of M-class flares and you extrapolate, you will know what your chance of seeing an X-class flare is. So there is some real practical value, predictive value in this power law. Even if we can't understand it any more than we can understand why earthquakes have the power law, that is a very similar kind of thing that people do with earthquakes. And they will say, given that we're building in Bozeman, Montana, which has a very low power law curve here, you can extrapolate it out and say, once every 100 years, you're going to see a magnitude 6 earthquake in this location. We have built a building that will withstand a 100-year earthquake. That's what they mean by that. They're using this power law and extrapolating into the future and saying that is how likely something that big is based on the power law, even though they may not have ever observed such a thing. And here you're using this as forecasting tool. So you haven't observed the X-class flares, but you say, we saw a lot of C and M-class flares, we extrapolated. There is a 50% chance of an X-class flare tomorrow. All right, I think I've actually finished early, which is not bad because I've been talking at you for 3.5 hours. So with that, I will pull back and just entertain discussion or questions. Anything. Robert, yes.
Yeah. So if we scale down flares in their flare strength,
Right.
Is it still like the same process which is going on, just smaller? And when does it break down?
When it breaks down, I don't know. You may be aware that, yeah, I showed you the large end because we're talking about societal impacts, but if you go down to the small end, you have flares that, you know, if you extrapolate that, this is what you get into microflares or nanoflares that could be happening all the time, literally, you know, hundreds per hour if you get to a small enough scale. If you just extrapolate that, that is one hypothesis for what is heating the corona all the time. Sadly, if you look at the power law I showed you, it actually ends up not really contributing that much extra power because it's a power law that was a negative number larger than 2 or a power less than -2, if we want to say that. So that part is still unknown whether that power law keeps going or whether it turns up. Whether they're the same process, that's, you know, that's an important topic that one needs to keep discussing. We don't know the answer to that. This standard model of a flare is premised on reconnection at a current sheet. Is a microflare, which is a very small brightening, say in the corona, caused by reconnection at a current sheet. I have written papers that say it is. I have learned that just because I write a paper about it doesn't make it true. So there are other people who think that no, it's a different process. I guess I'll just have to leave it that way. We all know that's how science works, right? It's not like addressing the public where when the scientists say they don't know, that they see all sorts of conspiracies. This is just the way we work. We don't yet know if the small scale energy releases, which clearly are going on all the time, are the same process of magnetic reconnection at a current sheet that a flare is believed to be.
So if we analyze flares, are we typically only considering X and M class flares, or are there also some?
Oh, a lot of good work is done on flares, certainly of C class. I've written many a paper on a C class flare. Many people will say those flares are much easier to study. If you have an instrument like AIA or even IRIS, a lot of the measurements you're making saturate when things get too hairy. So no, it's certainly goes down to C class and even below that. I think below that, people then are starting to talk, like I was saying, into that regime of it's less a flare and more of an, you know, brightening in an active region, right? But given what I just blathered on about, you'll understand that maybe those are the same thing, right? It's just a matter of scale. Yeah.
Thanks.
Yeah.
Dana Krishna has a question in
Yes,
chat.
please. Oh, I think I should I can now go to this other view. Okay, good. Right. Krishna, yeah.
Yeah, so the power law of that different flares were shown
Yeah.
falls from the power law at higher fluxes. So I was thinking, why is it deviating from power law at higher fluxes?
Oh, excellent question. Right. So maybe so you're talking about this point here, right? Can you see? Oh no, sorry, I'm not sharing my screen. It's been a long day. Yeah. Okay. You're talking about this place here. You can see my mouse now. Is that what you're talking about? Like out here?
I think he means the higher flux.
Yeah, this is the highest flux.
Oh, right. Yeah.
Yeah. Yeah. Any student out there want to just shout out what they think might be going on? The error bars are a clue.
You don't have enough samples there, maybe?
Yep. Yeah. In fact, the way this is done, you can see what goes on at this. Oops. Sorry. I don't know. There we go. Sorry, I had to mute you. This is the good old Halloween event, right? X4 or something like that. There was one of them. It gets counted once. And it didn't, nothing that big happened in the cycle before or the cycle after. So this is really not saying that this is the largest flare you could ever have. It's just saying that the frequency is so low that in our 30-year data set, we got one. And we somehow didn't see any in the bin below. Maybe we should have expected to see two. That's 2 plus or minus, you get the idea. So it's quite likely this keeps going. There is actually a lot of interest, and the text goes into, I think, more detail. Carl Schreiber did some excellent work just sort of saying, you keep going, you're going to get to what would be like an X100 flare. And based on this, you'd predict how frequently that would happen. And I've forgotten, that particular number might be one every 3,000 years or something. So clearly we haven't made enough observation to definitively say whether X100 flares happen once every 3,000 years or less frequently than they're supposed to. There's small number statistics, undersampling. Yeah. So nobody knows that it turns over. It stands to reason you can't produce, yeah, you can't produce flares of arbitrarily large size, but no one's definitively shown that where that rollover is. Yeah. Sorry.
So my question can be a bit off track. I just remembered that I was asked a question sometimes back. So it goes like, if an hypothetical sun, if the temperature of normal corona is 100 million Kelvin instead of 1, would it make any difference in flaring processes and its different scales? I didn't have any answer that time. So.
Yeah, I did not review, well, but we can go back to the basic question of why the coronal temperature is what it is. And we have these loop scaling properties, and we would have to assume that if the if this hypothetical sun had a higher temperature, it still satisfied the same processes of thermal conduction and radiation. So if it were 100 million Kelvin, what would the thing in your scaling law have to be? What would you have to change to make that temperature go up? You remember your scaling? This is the activity we did, one of them. I said it was 3 million, and then you derived epsilon, right? Mm-hmm. So if I had said, oh, it's 100 million, okay, you would derive an epsilon that was a whole lot bigger. You'd have to have a heating rate that was a whole lot bigger. What we didn't go into is that heating is probably due to the magnetic field of the sun. So either the magnetic field strength is a lot higher, or there's a lot more energy, wave energy or some kind of energy traveling into that magnetic field. But if you had much bigger magnetic field strengths, then you would also have much bigger flare energy flux releases. We did derive the fact that those scale. So by most estimates, yes, the answer would be you'd have much bigger flares. Basically, as a roundabout, you must have much more heating going on at all times to keep it at 100 million Kelvin, and you'd have to have very strong magnetic fields to provide that heating, and that would be the same thing that would supply flare energy.
Oh, yeah. Thank you.
Yeah, you're welcome. Wait, Elizabeth, you have your hand up, or Liz? Or is that an accident? You're muted right now.
Yeah, no, I do. So I'm guessing the answer is probably no, but is there any contribution to the cooling rate or anything like that from energy going into the chromosphere via condensation or anything like that?
Condensation. Tell me what you mean by condensation.
The opposite
Sorry.
equal reaction to having an evaporation. The
So yeah, that would happen afterwards, right? The draining of the loops, and
notice
yes.
the way I understand it is that, like, so you would have, so my work is in the electron beams. So you would have, after the reconnection, you have energy deposition at the chromosphere,
right,
which heats it up and you have a pressure gradient. And so you have evaporation also from that. And then
right.
The condensation being pushed downwards, condensing material.
Then, okay, so I just wanted to make sure you're really talking about chromospheric condensation, which is a term of art. It has nothing to do with the condensation that forms on your window pane on a cold morning. But it's a term that has to do with, it's basically the back reaction. We were talking about energy going up, but of course there's also momentum, which is an upward momentum from the, of the material that's evaporating into the chromosphere. And due to one of the few laws I just will never allow to be violated, Newton's third law, there must be an equal and opposite back reaction, and that is this downward pulse, the chromospheric condensation. It does not carry a lot of energy though. It carries momentum down, but it's not a big contributor to the energy. And in the, I did a very simplified picture of the energetics of these flares, but in that picture you just spelled out, which is that the energy is carried down not by classical thermal conduction, but by non-thermal particles. They deposit their energy in chromospheric material, and they heat up that chromospheric material. And except for the energy they lose directly through radiation, the material they've heated up is now coronal material because it's hot. So this also falls into my glib rule of that actually did not lose, you did not lose any energy that way. All you did was gain mass. And you've redistributed that energy over more mass. And so rather than having, 10 kilovolt particles, which are few in number, you have a lot of 10 megakelvin plasma. Does that make sense? But the back reaction that goes down is important, and it's actually something I've been spending a lot of time researching, but energetically it is not important. Based on
that's kind of what I thought, but wanted to check.
No, it's an excellent thing to think about though. So we always want to ask exactly those kinds of questions. Like, well, is this, can I show that this is or is not important? Is this James, I think?
Hi.
The next person? Yeah.
Yeah, so I'm going to reference your image of the standard model for the solar flare, which had the CME. Coming from a magnetospheric perspective, it looked a lot like, obviously the scales are very different, but it looked a lot like reconnection in the magnetotail and the release of plasmoids, being analogous to the CME. But my question was towards the reconnection site. So in the magnetosphere, the reconnection in the tail is driven by, increasing magnetic flux from convection. I don't know if we'll cover this later in the week, but what's the kind of cause, of the sort of pressure into the reconnection site?
Excellent question. And I'll also say this is this analogy that you're drawing on is one that Carl Schreiber always tried to focus on, how the similar, in fact, I think I was writing one of the chapters and he pointed out, he goes, if you take, I'm going to share my screen again just so I could illustrate what I'm trying to say here. And yes, if you take this cartoon and rotate it clockwise 90 degrees, it looks like the Earth's magnetic field and the magnetotail and reconnection, yes. And the the precipitating event in this, the standard model, that is similar to, I think, the sort of solar wind dragging the magnetic field open is this coronal mass ejection that has dragged the flux open. So that in this standard model is, I think, answers your question. That's what drags that's what creates this big magneto-tail-like structure. What starts the reconnection? Is that what you're asking? Why does all of a sudden this X point form and start what you would call, I believe, I might be misusing the terms in the magnetospheric side, dipolarization.
Yeah, exactly. Yeah.
You think of it as,
that was something similar, but my question was kind of towards the inflow part.
Yeah.
So and you said that the CME drags the kind of tail out.
My answer, but I will say I am a minority in saying this, but I argue it every chance I get, is the inflow is caused by the outflow. When you reconnect a field line, it shoots out of this little narrow jet and sucks stuff, and stuff has to take its place. That's just as simple as that. It just really, when you snap this stuff out, and you snap it out because the magnetic field line you've created is strongly bent. I don't show it here, and therefore has to, retract under magnetic tension very rapidly at the Alfvén speed in these models. So the answer to what drags in the inflow is simply that it needs to take the place of the stuff that was disappeared through the outflow.
So it's kind of like a feedback on itself, almost.
I guess.
But yeah, thanks for that. That's,
sure. I mean, as I said, this is not a universally accepted idea, but that's the picture I've generally come away with. Let's see.
Dana, are you available for office hours after this?
I am, and afterwards is coming up very soon.
Okay, great. I have some final closing instructions.
Oh, okay. I will turn it back over to you then, Nick.
That'd be great.
All right.
Okay, so one. So here I'm gonna copy and paste this into the chat so that we can all see all my points. There we go. Okay. First, survey. So because this is a new format and we want to make sure things are working well, we're 3 days in. I figured this was enough time to test out everything and work out all the kinks. I'm going to send out a SurveyMonkey poll later this afternoon, asking you a bunch of questions about how things are going. So please respond to that. That survey will be anonymous. It'll simply be tracking whether you responded or not, so that I can bug you if you haven't responded. So if you could do that in the next 24 hours, that would be great, so that we can get some feedback and make any adjustments that we need to make on the fly. So this afternoon, your time zone groups will work on the next lab, which is posted on the schedule. And we'll be doing we'll be finishing that off tomorrow, but this afternoon you'll work on parts 1 and 2 for that lab. I think right now only part 1 is identified on the schedule. Whoops, something just went horribly wrong. All right, well, I will try and fix that. But please work on parts 1 and 2. Part 3 we'll do tomorrow in the synchronous session in your synchronous groups. All right. Also on Saturday we have on the docket is student presentations. So you all presenting on your research. The way that's going to work is we're going to try and run a virtual poster session. And so you don't need a poster but you should have a short talk prepared if you want to present. I would say no more than, certainly no more than 10 slides, probably closer to 5 slides. And you'll spend a little bit of time in the breakout rooms, and we'll probably do some, allow people to rotate through breakout rooms, and we'll give you more details about that, how that's sorted out. In any case, what you need to do if you intend to give such a talk, please send Tammy a title as soon as you can. And Tammy, you want to say what you just said out loud?
Yes, what I will do this afternoon is I'm going to send you the link for the folder to upload all of your talks. And so if you have any trouble, just go ahead and send them to me, okay? So we should be all good. And also if you have any questions, let me know. Thanks a bunch.
Yeah, but if you are intending to talk, so you can even decide now, but let us know as soon as you can so that we can make sure that we've got it scheduled appropriately. Jeff, you had your hand up.
Yeah, sorry if you already covered this and I just missed it, but just to be clear, the lab 2, you want us to actually do part 2 as well before tomorrow?
Yes, please.
Okay, thank you.
Actually, on that note, are there supposed to be 2 links there? Because I only see 1 link for like lab 2, not for the.
It's all one document. Okay. Any other questions? So, survey, lab, title to Tammy for your talk. Alessandro.
I just don't remember the time we have for the talk. 5 minutes?
So for the talk,
yeah.
So we're playing with a slightly different format. I would plan for like a 5-minute talk, but it's going to be, we're going to be doing it in a more informal format. So you sort of introduce your material. So think of it as if you're presenting a poster, though you would want to do it with slides in this case. Okay. Okay. And then hopefully that will generate some discussion around the, have an opportunity for discussion. All right. Anything else? Oh, yeah. Prabir.
Yeah, you said the talk would be on what we work on, but it is it like what we work on in general or what we have worked on in this school so far?
No, something your research. So what you're working on in your home institution.
Ah, oh, all right. Okay.
Great. Anything else? Okay, great. I think we're done. If you want to hang out for Dana's office hours and ask him more about various aspects of solar physics, that's great. And if not, we will see you all tomorrow.
Yes. See you all tomorrow.
Bye.